Hi everyone, in this video we are going to do some linear algebra stuff. We have this matrix A, which is of size 2 by 2 with real elements. Here the elements of the matrix are real numbers, and we want to do the following things. First, we want to diagonalize the matrix A, this matrix over there, and then we want to find the powers of A squared, A cubed, and A fourth using the diagonalization from question 1. First of all, the diagonalization is like this VD times V1. We can write the matrix, there is a theorem, but I'm not going to go into a lot of details there. We have this matrix A, and this can decompose into V times D times V to the minus 1. And this is V1, V2 times lambda 1, lambda 2, 0, 0 times V1, V2 to the minus 1. What is this D? This is a diagonal matrix where here we have the eigenvalues of matrix A. V1 and V2 are the eigenvectors. V1 is the eigenvector corresponding to eigenvalue lambda 1, and V2 is the eigenvector corresponding to the eigenvalue lambda 2. So here we have the V1, the column, we have the column of the eigenvalue in the first column of this matrix, and in the second column we have the second eigenvalue. Okay, let's find the spectrum of the matrix A. In other words, let's find the eigenvalues. To find the eigenvalues, we form this A minus lambda I. So we have our matrix 1, 2, 2, 1 minus lambda times, this is the identity matrix, so it would be lambda 0, 0, lambda. And this is equal to 1 minus lambda, 2, 2, and 1 minus lambda. The characteristic polynomial now. Is the determinant of A minus lambda I. So it's the determinant of A minus lambda I. So it's 1 minus lambda, 2, 2, 1 minus lambda. What is the determinant of this quantity? It's 1 minus lambda squared minus 2 times 2. So it's lambda minus 1 squared minus 4. We can use the identity, so we can write lambda minus 1 minus 2 times lambda minus 1 plus 2. This is lambda minus 3 times lambda plus 1. Now the root of the characteristic polynomial, what are the roots? We have to take lambda plus 1 is equal to 0. So lambda 1 is minus 1, this is the first eigenvalue, or lambda minus 3 equal to 0, so lambda 2 is equal to 3. So the spectrum of the matrix A is lambda 1 and lambda 2. So it's minus 1, 3. The other step is to compute the eigenvectors now. So we have to compute the eigenvectors, and what do we do? So let's write the spectrum again is minus 1 and 3. Yes, it's minus 1 and 3. So we form now alpha minus lambda 1 I times xi, which is a vector, equal to 0. So we have 1 minus lambda 1, 2, 2, and 1 minus lambda 1 times xi 1 and xi 2 equal to 0. So this is 1 minus minus 1, 2, 2, 1 minus minus 1, xi 1 and xi 2. So this is just 2, 2, 2, 2. Xi 1, xi 2 equal to 0, 0. So what we obtain from there is 2 xi 1 plus 2 xi 2 is equal to 0. 2 xi 1 plus 2 xi 2 is equal to 0. It is evident that this is just xi 1 plus xi 2 is equal to 0. So the eigenvector v1 is of the form xi 1, xi 2. So is xi 1 and xi 2 is minus xi 1. So it is xi 1, 1 minus 1. So let's put xi 1 equal to 1, okay? So this gives that the first eigenvector is 1 minus 1. This is our eigenvector. Now let's take the second eigenvalue, lambda 2 equals 3. Should be 1 minus lambda 2, 2, 2, and 1 minus lambda 2. We want to find the second eigenvector, xi 1, xi 2, equal to 0, 0. So it's 1 minus 3, 2, 2, and 1 minus 3. Xi 1, xi 2. It's minus 2, 2, 2, and minus 2. We obtain that minus 2 xi 1 plus 2 xi 2 is equal to 0. And 2 xi 1 minus 2 xi 2 is equal to 0. From here we just obtain that xi 1 is equal to xi 2. So the eigenvector v2 is xi 1, xi 2 is equal to xi 1, xi 2 is equal to xi 1. So it's xi 1, 1, 1. Let's put xi 1 equal to 1, so the v2 will be 1, 1. Now let's write our matrix. A is equal to v1, 1 minus 1, 1, 1 times d, what is the eigenvalue lambda 1? Minus 1, 3, 0, 0 times, we need the inverse of this matrix, 1, 1, minus 1, 1, the inverse. It's 1, 1, minus 1, 1 times minus 1, 0, 0, 3 times the inverse of this matrix. So is 1 over the determinant of this, 1 over 2 times, we exchange these elements here, so it's 1, 1, and here we change the signs, we flip the signs, so it's minus 1, 1. So A is 1 over 2 times 1, 1, minus 1, 1 times minus 1, 0, 0, 3 times 1 minus 1, 1, 1. We have completed the diagonalization. Now let's see if this gives us the matrix 1, 2, 2, 1, if this gives us the original matrix. So it's 1 over 2. Let's multiply first these two matrices. So we should get here minus 1. We multiply this with this row with this column. Minus 1, 3. Then we get 1. Then we get 3. Times 1 minus 1, 1, 1. So it's 1 over 2 times, let's do the calculations, minus 1 plus 3. Then we have 1 plus 3, 1 plus 3, and minus 1 plus 3. So it's 1 over 2 times 2, 4, 4, and 2. So this is 1, 2, 2, 1. We have a scalar multiplying a matrix, so this scalar will go inside and multiply all the elements of the matrix. So it's 2 over 2, 1, 4 over 2, 2, 4 over 2, 2, 4, 2 over 2, 1. So we get this matrix there, right? Let's put in a box here the diagonalization form for question 2. So what was question number 2? To find a squared, a cubed, and a to the power of 4. Okay, so a is 1 over 2 times 1, 1, minus 1, 1 times minus 1, 0, 0, 3 times 1, minus 1, 1, and 1. So let's take a squared. So this should be 1 over 2 times 1, 1, minus 1, 1 times. Now here we have to pay attention because it's minus 1 squared, 0, 0, and 3 squared. There is a theorem that allows me to do that, but I'm not going to put the details and the proof. So when you just raise the diagonal part here to the power of 2. So this is 1 over 2 times 1, 1, minus 1, and 1 times, this is just 1, 0, 0, 9 times 1, minus 1, 1, and 1. 1 over 2 times, let's do some the multiplication of this matrix and this. So this is just 1, then we get 9 minus 1, and 9 times 1 minus 1, 1, 1. This is 1 plus 9 minus 1 plus 9 minus 1 plus 9, and 1 plus 9. So this is 1 over 2 times, this is 10, 8, 8, and 10. Okay, now this is 5, 4, 4, and 5. So a square is 5, 4, 4, and 5. Over there. Now we can do the a to the power of 3. So it should be 1 over 2 times 1, 1, minus 1, 1. Now this this one should be minus 1 to the power of 3 to the third power, 0, 0, and the other eigenvalue is 3 to the power of 3 times 1 minus 1, 1, and 1. So this is 1 over 2, 1, 1, minus 1, and 1 times, this is minus 1, 0, 0, 3 to the power of 3 is 3 times 3, 9, times 3, 27. One minus 1, 1, 1. This is 1 over 2. Now this should be minus 1, 27, 1, and 27 times the other matrix. So this is 1 over 2. We are almost there. Minus 1 plus 27. 1 plus 27. 1 plus 27. And minus 1 plus 27. This is just 1 over 2 times. This is 26. 28. 28, 26. So this is 13, 14, 14, 13. So we have computed a to the third power, raised to the third power. It's 13, 14, 14, and 13. It's a straightforward calculation. Let's go to a to the fourth power. A to the fourth power is 1 over 2 times 1, 1, minus 1, and 1 times. Now we have minus 1 raised to the fourth power and 3 raised to the fourth power. And we multiply with the other matrix, 1, 1, minus 1, and 1. Sorry, it is 1 minus 1, 1, 1. So this is 1 over 2 times 1, 1, minus 1, 1 times. This is just 1, 0, 0. So this is 3 to the fourth power, 3 times 3, 9, times 3, 27, times 3, 88, 81. Let's do the multiplications. So this is 1, this is 81, this is minus 1, 81. So this is 82, 80, 80, 82. 82 over 2, 80 over 2, 80 over 2, 82 over 2. This is 40, 41, 40, 40, 41. There. So we have completed our little application. Just do a quick review of the application. We were given this matrix, so we do the spectral decomposition of this matrix, where this product is equal to A. So this is just a matrix containing the eigenvalues V1 and V2. These are the two columns here. Lambda 1 and the lambda 2 are the eigenvalues of this matrix A, and this matrix is just the inverse of this. The first step is to find the characteristic polynomial, find the eigenvalues lambda 1 and lambda 2, so this is the spectrum. Find the associated eigenvectors taking A minus lambda 1 I times xi equal to 0, so we obtain the first eigenvector, and then we obtain the second eigenvector. We go back and substitute. So these are my eigenvectors, these are my eigenvalues, and this matrix is the inverse of this matrix. I go through doing some trivial computations there. So the inverse can be easily computed. You just the inverse of this is very easy. It's 1 over the determinant of the matrix. So 1 over 2 times, we exchange these elements, so this one goes there and this one goes over down here. And we flip the signs, so this should be -1 and this should be 1. It's very easy, you can verify by yourself. We have this again decomposition, so we have this form of the matrix A, and then we go step by step to compute the powers A squared. We compute A squared, which is 5, 4, 4, 5. We compute A cubed over there, which is 13, 14, 14, 13. And last but not least, we compute A to the power of to the fourth power, so it's 41, 40, 40, 41. This is very significant application because as you know, when you want to compute a matrix to raise to 1 power, so when you want to compute A square, you have to write A times A, so A cubed will be A times A times A square times A to the power of fourth will be A times A times A times A. So it's A to the third power times A. Therefore, here with this eigendecomposition we avoid this to do these calculations which could be very long calculations, and instead, so imagine that you want to compute a to the power of 1000. You have to multiply a times a times a times a and so on. You have to do multiple multiplications. So with this diagonalization process, you avoid all that and you can compute the powers easily, but it's not in every possible way this applicable, because you have to consider the matrix, not you have to consider what matrix that you have. There are some examples that some matrices are not diagonalizable. You cannot diagonalize, so you have to be careful. This is just this application is just very simple, but bear in mind that it's not a solution for everything just to diagonalize. You have to take into account what is the matrix that you have. This is just a 2x2 matrix, therefore there is no problem to go through. It's just a 2x2 matrix with real elements of the matrix. But be careful, it's not for every possible situation. You can try with another matrix like you can try with this matrix. Try this matrix and see, can you diagonalize this matrix? This was the basic example. It's good to show some linear algebra stuff, and I hope that you enjoyed the video, and I will come up for more videos in the future. I will upload more videos. This is just a brief well, the process is simple, but you have to be careful doing not missing any sign when you do the multiplication of the matrices. You have to be careful. So if you do it step by step, then there should be no problem, I think. Thank you again for your attention and for your time, and if you have any request, I'm looking forward to hearing from you. Best wishes, and I hope that you are doing well.